Right, thanks for having me. I'm pretty excited to be here at WOOT today. This is my first academic presentation. So my name is Jonathan Brossard. Half of my time I'm a PhD student at the Conservatoire National des Arts et Métiers in Paris. The second half of my time I'm an associate professor at the Conservatoire National des Arts et Métiers. And the two other halves of my time, I work at a cybersecurity startup called Moabi, where we perform in reverse engineering to help secure industrial goods like satellites and cars and things like radars and submarines and so on and so forth. I come from the industry, and before being an academic, I used to work at Salesforce, where I've been the principal engineer of product security, as well as the director of the red team. Okay, so today I'm going to introduce you a little bit to a concept called SBOMs, Software Bill of Materials. Then we're going to talk about Libification, and we're going to see how to transform essentially an executable into a shared library. So if you have questions, please keep them for the end of my talk. Motivation. So Software Bill of Materials. It's a new tool in the toolbox of product security people to keep track of software components inside complicated software. So for each component, typically as exemplified on the right, we keep track of either a CPE, Common Platform Enumeration entry, and for the software who never had a CPE because they never had a vulnerability, we can extend that using what's called package URLs, or PURLs for short. So you can see on the right, for instance, we have an entry for OpenBSD, OpenSSH, and this OpenSSH version being 9.6p1. We can match that against the entries of the NIST. CV is nowadays having a dictionary of vulnerable CPEs. So this allows us to do an automated vulnerability assessment based on the versions of the software. They're becoming ubiquitous. The executive order on cybersecurity by President Biden mandates that they're being used. In Europe, there's an upcoming regulation called the Cyber Resilience Act, which also mandates that if you want to sell IoT goods in Europe, you must provide the software bill of material to your clients. And there's more industry-specific guidance as well, like the FDA has one for medical goods in the US. And car industry, for instance, they've been working on the ISO 21434 for a number of years, which also mandates software bill of materials. So they're useful, they're cool, and they allow you, based on version numbers, to determine, okay, do we have a potential vulnerability in software? The drawback is that they don't scale too well. I'm showing you a number of scans I've performed, and just looking at like the new vulnerabilities appearing in this software, in those car firmware SBOMs, we see thousands of possible vulnerabilities. So the question that arises is, based on version numbers, there appear to be vulnerabilities. Are they true? When you speak with third parties or with programmers, they're like, okay, you're telling me there's a vulnerability. Can you actually prove it? So that's what we're going to try to solve today. Instead of writing full exploits, we're going to try to work on partial proofs of vulnerabilities. So how do you prove vulnerability nowadays? Well, in short, to paraphrase Alva Flake, if you want to prove there is a vulnerability, you write an exploit. We can split writing an exploit into three main steps. The first one is to reach the vulnerable function. The second one is to trigger the vulnerability. And the third one is to achieve code execution and weaponize the exploit. When I'm talking about exploits here, it's mostly in compiled software. So we're talking mostly about memory corruptions, which make up for 70% roughly of exploitable vulnerabilities in software based on the data from Microsoft and Google. So the little bit of a problem here is that the first step alone, reaching the vulnerable function, It's called the reachability problem, and it's known undecidable since the PhD thesis of Gordon Rice in 1953. So we've been knowing that this is an undecidable problem for 70 years. So if you're asking product security teams to do that like multiple times a day, to verify 1,000 vulnerabilities, you're asking them to solve undecidable problems 1,000 times a day. So instead of doing that, what I'd like to do with this talk is to offer a new way to prove vulnerability without writing an entire exploit. So to do that, we're just going to try to focus on triggering the vulnerability without creating an input that can reach the vulnerable function first. So we'd like to call just the vulnerable function directly. To do that, we're going to transform the vulnerable function. So I'm going to limit in my talk the scope of my talk to Linux applications on ELF formats. What we'd like to do is transform the application into a shared library so we can call any function inside the shared library directly, therefore avoiding the reachability problem. To do this, we're going to introduce a new concept called Libification, which is the fact of transforming something into a shared library. So this is a typical C compilation problem where we have a source code which is compiled into assembly code via a compiler. An assembler produces object files, and a static link editor produces either shared libraries or executables. If you think reverse engineering, the first thing that comes to mind is probably disassembly, which is taking the executable or shared library and going back to assembly code. Tough luck, this is also undecidable. So let's not do that. If you think decompilation, which is the fact of going back to source code instead, if you're not too familiar with the concept, there's a great introduction by Cristina Cifuentes and a PhD thesis from the University of Queensland. Is a good reference from 1994. Well, compilation builds on top of disassembly. So that's also going to be undecidable, and let's avoid to do that as well. So most simply, what I'm offering to do today is to create a tool which performs libification and transforms an executable into a shared library. So if we take executable and shared libraries and look at like the standard defining them, how do they differ? Well, they look a lot alike. In particular, all the sections which are loaded into memory, which are called proc bit, are the same. Like they have an executable section, a data section, a number of relocations, and they look very much the same. So the work to be done today is, can we modify the remainder of the application that is not loaded into memory, the various ELF headers, to transform an executable into a shared library? It's a good idea, isn't it? So let's try how to do this practically. So we started with a libification oracle. The idea in this slide is basically we're going to take an application. We took binls from core utils because it's a simple ELF binary. We try to load it through dlopen, which is a primitive from the dynamic linker to load shared libraries at runtime. Think of it as a plugin. We look at like, did that work? If it worked, well, we do have a shared library, a valid shared library. If it doesn't, let's look at like the error reported by the dynamic linker through dl error and try to modify further the executable until that gets accepted. So the first thing to do is to look at the main ELF header. You will notice that I'm reproducing here 64-bit versions of them, but the same thing works with 32-bit versions as well. So the third thing to do is to transform an etexec into an etdin ELF type, because a dynamic linker will not accept to load an etexec binary. Then we're going to walk through the dynamic section of the application. So to find the dynamic section, either the application has section headers, and we just look for the one which is of type SHT dynamic, or if the section headers have been removed from the application, we can look at the segments and look at the PT dynamic segment And thankfully, they coincide, the dynamic section being exactly the dynamic segment. The dynamic section is comprised of a number of structures, like reproduced here. And we're going to patch some of them. So there's a number of new flags that did not exist like 2-3 years ago when I started this application. But Ingo Molnar, responsible for the toolchain at Red Hat, introduced a few new flags to basically prevent us from doing this trick of loading an executable as a shared library. So we're going to need to nullify in the dynamic section the entry called DT bind now. If you're familiar with it, it's a protection against certain classes of exploits by producing relocations which are resolved at execution time, at load time, instead of performing lazy binding. And this allows to have a global offset table which is remapped static instead of remaining writable into memory. There's a couple other flags that we need to zero out. So in the DT flag, we need to remove the DT open and df1 PIE flag if present. Optionally, we can remove the constructors and destructors of the application. You wouldn't expect that to be called in a shared library, and it can trigger unexpected segmentation faults at times. So to automate that, we have produced a tool which is called the witchcraft linker. It does perform a bit of witchcraft. It takes an application, in this case LS, patches it, and as you can see, it produces a shared library. This tool is open source and published under MIT and BSD license, and you are welcome to contribute. Interestingly, the application still runs after being patched. I'm not going to go into the details, but feel free to ask me a question about this. It's interesting. In terms of validation, so what we did is take all the binaries from a Ubuntu distribution on an Intel 64-bit architecture and try to libify them. So there's about 435 binaries on a default installation. And libifying all of them so they can be accepted by DLOpen took about 3 seconds in total. In conclusion, so we saw that disassembly and decompilation are undecidable techniques. So instead of doing this, what we'd like to do is transform executable into shared libraries. This is a new process called Libification. You might be wondering, is it possible to go back instead to object files to undo the work of the linker? So there's an interesting PhD thesis from Capelletti in Polytechnique Milan from 2017 that did this. And incidentally, we have a tool called the Witchcraft compiler that attempts to do the same. Once we manage to transform an application into a shared library, we can call arbitrary functions inside it. We don't necessarily have the full prototype for them, but by using a simple interpreter and performing a reflection, we can call those functions directly from, in this case, a Lua interpreter. And this is a new tool called the Witchcraft shell. On the screenshot, you can see that basically we are loading Apache into the memory of this debugger called the Witchcraft shell. It loads the application into its old address space using DLOpen, and then we can call arbitrary functions from Apache directly. So in this case, we are calling the app-get-server-banner function. Notice that I don't actually know its prototype, but if I print what is written by this function, you can see the banner from Apache, meaning we have borrowed a function from Apache. This tool is also under MIT license, and feel free to contribute to it. Finally, the fact of being able to call arbitrary functions directly, so we call that procedural debugging, allows us to create small scripts that can test for vulnerabilities. So that's what we'd like to automate in the future. On the slide, you can see that there is a particular vulnerability called CV 2022 3786, which is an OpenSSL vulnerability. We wrote a 5-line script that allows for testing using Libification and procedural debugging. If a given compiled archive, static library, is vulnerable or not to this particular vulnerability. So in this case, we have tested against version 308, 307, which are not vulnerable of OpenSSL. And you can see that version 306 is vulnerable. So that's what we'd like to generalize. So instead of writing 1,000 exploits for the Tesla firmware we saw earlier, we just write scripts like this, and hopefully we manage to generate them automatically in order to prove exploitability and to prove the presence of vulnerabilities inside software. Well, that was it for me. Thanks for your attention today.